Right, I'm Joshua Zelinksy, a lecturer in the math department. This talk is going to be on integer complexity. This is a pretty simple problem. All right, so some numbers feel more complicated than other numbers. 1 feels pretty simple. 2 to the 20th feels kind of complicated, but not that complicated. You've got an easy way of writing it down. 2 to the 20th plus 1 feels a little more complicated. Right? But if I wrote down some number that looked completely random to you with like 100 digits, that would feel really complicated to you. All right, so in some sense we have an intuition that how complicated a number is depends both on how big it is and how easy it is to describe, as those somehow balance out. Okay, so mathematicians have been trying for a while to come up with different metrics of how complicated a number is, and then say, what can we say about that? And this closely connects to 2 problems of interest, one of which is that people want to make mathematically precise notions of Occam's razor, and it turns out that having some notion of complexity in this sense, how complicated something is closely connected to that. And the second thing is some versions of this turn out to be connected to, if you've heard of the P equals NP problem, turn out to be connected to that, although the connection's a bit subtle. Okay, so we're going to define the complexity of a number as the minimum number of ones needed to write n just using addition and multiplication. So for example, I can write 6 as 1 plus 1 times 1 plus 1 plus 1. And that shows that the complexity of 6 is at most 5. And if you play around with 4, 3, or 2 ones, you'll convince yourself pretty quickly that you can't write 6 using fewer ones. I should add, just because this sometimes comes up as a question here, no, you aren't allowed to do things like writing 2 ones next to each other as 11 or anything like that. Sometimes a variant of this problem is actually done as if you have 7th or 8th grade kids, it's called the 4 fours problem, where they're supposed to make every number from 1 to 100 using 4 fours, and they're allowed any operations they can come up with. And we need a precise notion, so no, just addition and multiplication, nothing else. Okay, so there are classical results that if n is greater than 1, we can bound the complexity by 3 log base 3n and 3 log base 2n. So the lower bound comes from an induction argument, and the upper bound comes from writing n in base 2 and then doing what essentially turns out to be the obvious thing. I should also note that the lower bound induction argument does not come from writing n in base 3 directly, which is a common misconception when you give a longer version of this talk. So I need to say that so no one tries to get that sort of argument to work that way. Although it is a fun exercise if you care about that. All right, so can we do better? Yes. We can get, in fact, the complexity of n is at most 3.781278 times natural log n, which is a little bit smaller. This is due to work by myself and Harry Altman, who's at the University of Michigan. I should note that the way you do this is you can't just write n in a single base. If you try to write in a larger base, it becomes less efficient. But it turns out if you use other bases, you can tactically switch between writing your number in different bases as you make it write in terms of smaller and smaller numbers. And if you use this for bases p equals 2, 3, 5, 7, 11, 17, 13, and 19, then you'll end up having that you'll actually get the bound there. And I should note that that lists all of the primes up to 19. It's not that you got bored at 23, but 23 is actually a technical failure. All right, so that's just one of my projects. Thank you very much.